Hello everyone, I am Dr. Naresh Kumar, working as an assistant professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on power BJT, bipolar junction transistor. So now here in this, I will explain first basics of power BJT and next symbol of power BJT. After that, structure, construction of power BJT, the working of power BJT, and next input characteristics of power BJT, output characteristics of power BJT, and next switching characteristics of power BJT, next advantages of power BJT and disadvantages of power BJT, next last one applications I will explain. So now here first basics of power BJT. So now here power BJT is a bipolar junction transistor. The full name for BJT is bipolar junction transistor. So now it is having three terminals. The terminals are collector, emitter and base. Here the terminals are collector, emitter and base. Three terminals. Here the terminals are three terminals. Collector, base and emitter. And here we have four layers. So in the conventional BJT, we have only three layers, N, P, N only. But here in this, we have four layers. Another extra layer is N minus layer. So 4-layer device. And after that, next it is having two junctions. So now here two junctions means one is collector base junction and other one is a base emitter junction, two junctions device, and next is a unidirectional device. So it can allow the only a one directional current only, means its current always flows from collector to the emitter. So now here it is not bidirectional device. So now here it is a bipolar device and unipolar switch. So don't confuse here. So what do you mean by bipolar and what do you mean by unipolar? So here, so switches are classified into two types, unipolar and bipolar, and devices are classified into bipolar and unipolar. So now here coming to this, in the name itself, bipolar junction transistor means here the conduction in this, the current conduction is due to electrons and holes. Both electrons and holes. So such if current in the device, just because of electrons, both electrons and holes means that is bipolar. So now in case of FET, so that in that case only electrons are, some devices only holes. So just because of only electrons, conduction due to only electrons, conduction due to only holes. So such type of devices are known as the unipolar devices. Now what about the unipolar switch? Unipolar switch means here, so it can block only one polarity of voltage. So now in case of BJT, it can block, this is voltage, this is current, this is current and this is negative voltage. So it can block negative polarity of voltage. So now if it block both the voltage, positive and negative, that is bipolar switch. So example for bipolar switch is triac. And next here, so see the difference, unipolar device and unipolar switch. And next fully controlled device, it does not require to any external device to turn off the power BJT. So fully, so on off is in our control, turning on and turning off. So because of that reason, we can call this power BJT as a fully controlled device. And next here, current control device. So here, so entire output current and output voltage is depending on the base current only. So it is a current control device. So whereas power MOSFET is a voltage control device. And next, it is a non-linear device. The voltage current characteristics are not a straight line and not passing through origin. So that are non-linear characteristics that input output characteristics are non-linear characteristics. So because of that reason, this device is known as a non-linear device. Another name is, it is also known as an active device. So now bipolar junction transistor, 3 terminals, 4 layer, 2 junction, unidirectional bipolar device, unipolar switch, fully controlled device, current control device, non-linear device, active device. And next, another one is it has low current gain. And next, this voltage rating and current rating. Voltage rating is 1200 volts and 1800 amperes. And after that, it has only safe operating area will be in first quadrant only. So here, so in the previous one, so it blocks negative voltage. So it can block negative polarity of voltage. So here the safe operating voltage, safe operating area is first quadrant. Only here. Why? Because here this is current. So it is a unidirectional device. Current is always flows from collector to emitter. So unidirectional. So it will not allow the current from emitter to the collector. So now unidirectional. So in this region, so in the negative region, there is no current. And same way, it will block the negative polarity of the voltage. It will allow the only positive polarity. So here, this is the safe operating area. So now here is the first quadrant. Safe operating area will be in first quadrant. And next, it cannot withstand reverse voltage. This one, it cannot withstand reverse voltage. And it is limited to DC fed, DC to AC inverter and DC to DC chopper. So these are the basics. These things you need to remember. Just these are most important. And next, if we talk about the circuit symbol, the symbol of power BJT is exactly same as the of normal BJT, same as. So now here we have collector, emitter and base. Collector is represented with C and base is indicated with B, and E is represented with emitter is represented with E. And this is NPN transistor and this is the PNP transistor. See the difference here. The orientation, the arrow mark, the orientation towards the emitter indicates the NPN transistor, and the orientation away from the emitter is away from the emitter is known as a PNP transistor. So now here PNP transistor means NPN. So this is collector, this is emitter and this is the base. And next, what about this PNP? Collector, emitter and base is connected to N terminal. So now here throughout the analysis we will discuss only, we will consider only NPN transistor only. So now the real picture of this power BJT, it looks like this. And next, construction of the power BJT. So as we know, the conventional power BJT construction, we are throughout the analysis we are dealing with NPN transistor. This is collector, this is emitter and this one is the base. So here in the conventional BJT we have only 3 layers NPN. So now here in the power BJT construction, so if you see this construction, it is a vertically oriented structure. So vertical oriented structure increases the cross-sectional area. It maximizes the cross-sectional area, that will increase the current rating. So vertical oriented oriented structure. Vertical oriented structure increases the current rating. It is a vertical oriented. It is having 4 layers. So now here in this only NPN, the doping level is same, but here in the power BJT doping levels are different. So different types of doping level that we will see. So first the bottom layer is the N plus layer. So now this doping level, it is a highly doped layer. So that level of doping is 10 raised to the 19 per centimeter cube. So now here this layer is connected, this layer thickness is 250 micrometer, and next this layer is connected to collector. And same way here, same N plus layer is connected to, so this N plus layer is connected to this emitter. So N plus layer are connected to emitter and collector, and here is also same highly doped layer, and next that level of doping is 10 raised to the 19 per centimeter cube, and thus the thickness of this layer N plus layer is 10 micrometer. And next, what about this P layer? So now here this P layer level of the, it is moderately doped layer. So plus indicates the highly doped layer, and minus indicates the lightly doped layer, and no sign indicates the moderately doped layer. The moderately doped layer level of doping is 10 raised to the 16 per centimeter cube. So now it is connected to, now this layer width is 5 to 20 micrometer, and it is connected to the base. So now here the middle layer, now this one, in this layer is the N minus layer, lightly doped layer. The level of doping is 10 raised to the 14 per centimeter cube. So now this is connected to this both N minus and N plus. So now this N minus layer is also called as a collector drift layer. So now this collector drift layer width is around the width of the collector drift layer is depending upon the breakdown voltage of the power BJT. So now here that is around 50 to 200 micrometer. Now here another thing is here N minus layer. N minus layer is a collector drift layer. And next one more thing here. Now here this is N, P, next N minus and N plus. So this is collector, this is N plus emitter, and this is connected to the base. So now it is a 4 layer device. So plus indicates heavily doped, minus indicates the lightly doped, and next no sign indicates the moderately doped layer. So this is regarding construction of power BJT. So now here next the working of power BJT. So it operates in 4 modes. So first mode is the active mode and cutoff mode, and next saturation mode. Saturation mode, in this we have 2 modes. First one is the quasi saturation mode, and next hard saturation mode. So first cutoff mode and active mode, and next saturation mode. In the cutoff mode here, so here this is collector, this is emitter, and this one is the base. So now here we are giving the supply, some amount of supply is giving to this one. So now here this is VBE, and this one is the VBC, and next here this is VCE, this one. So now here see this one. So here we have 2 junctions. So this is junction collector base junction, and this one is a collector emitter base junction. So now here the 2 junctions. So junction, collector, base, junction. So these two are both are in reverse biased. So now BC and B junction, collector base junction and collector emitter base junction both are in reverse biased. So that condition is cutoff mode. In that the power BJT is in off mode. That means in this case power BJT is turned off. Active mode means, so now here, so VBE is for both are reverse biased. In both VBE is forward bias and VBC is reverse biased. VBC is reverse biased. So in the saturation mode, in the both quasi saturation mode and hard saturation mode, in this both junctions in forward bias condition. So now here, so in the active mode, this transistor acts as amplifier, and next here in the saturation mode, so here it will work. So the power BJT is turned on. It is in on position in the saturation mode. It is in off mode in the cutoff mode. It acts as a amplifier in the active mode. That we will see in the output characteristics of power BJT. So now here, this one, next, input characteristics of power BJT. So what are the input characteristics? What are the input parameters? What we are giving? So now here input voltage, collector, emitter and base. This is base current IB and this is plus and minus VBE. So now here VBE. So now this is VCE and this is VBC. So now here, if you apply some amount of voltage to this collector base emitter, and what will happen, some amount of current flows to this. If you draw the graph between this input current and this input voltage VBE and IB, so this current is in the around in the order of in the milliamp, and this voltage is in the volts. And if you draw the graph between, so the graph is exactly same as that of voltage diode forward bias condition graph only. Same, it looks like this. So see this one. So now here this is that cut-in voltage light. So this is the threshold value. Because of this transistor junction capacitance, it will not up to this. This is delay time. So now here, because of this, that reason, so now this is 0 and after that it will increases. And this is input characteristics of power BJT. And after that, next output characteristics of power BJT. Same collector, emitter, base, VBE, VBC and VCE, IB. And next here, this is IC and now if you draw the graph between output current and output voltage, so such graph is known as a, for different, these are the IB1, IB2, IB3, IB4, IB5, IB6. So IB6 is greater than IB5 is greater than IB4 is greater than IB3 greater than IB2 greater than IB1. So now here in this, so this is the cutoff region. So in this power BJT is in turn off mode, so it will not work. So now there may be, it is leakage current, this is leakage current, and next ICO. So now here, so now here I am increasing the I'm increasing the base current. So for a different base current, this one. And next here cutoff mode, VBE, these are in reverse bias. These two junctions are in reverse bias. So these two, this is in reverse bias and this one is in reverse bias. Two junctions, both the junctions in reverse bias. And here in the active mode, in this case, this transistor is in off mode. It will be in off and in the active mode. So here, so one is in forward bias and other one is a reverse bias. Which one is the forward bias? VBE is in forward bias and junction base emitter junction is forward bias and junction base collector is in reverse bias. So now in this case, so the power BJT acts as an amplifier. So now here increasing base current, and for maximum value of base current, after maximum value of base current, this collector current, it is the power BJT is into the saturation region. This is a quasi saturation region and this one is a hard saturation region. So what is the difference between quasi saturation region and hard saturation region? So first one is a cutoff mode, cutoff region, this one, and this one is the active region, and next quasi saturation region, this one, and this one is a hard saturation region. In the quasi saturation region, we can, in these two modes, so here this base emitter junction and next collector base junction both are in forward bias only. So now here in these two conditions, power BJT is turned on. It is in on condition. From the on to off, off to on. So from the quasi saturation, it can quickly we can quickly on to off or off to on. So now, so what about the so now for that case, quickly means we can use it for high speed, for fast response applications, and for high frequency applications we will use prefer quasi saturation. Hard saturation means, so it will delay time, so it will take some time to turn from on stage to off stage. So now for that case we will use this hard saturation. So hard saturation means here, so hard saturation applications are low speed and low applications. We will prefer hard saturation. So now here this one, so this is the BVSUS, and next here this is the VCEO, and next here this is one, and next here this is one VBO, B, and this one. So now VCBO. So now what is meant by BVSUS? So now here this one is the voltage collector emitter voltage that can be sustained. So when collector current is carrying the current, so such voltage is known as a VB sus. And next here VCEO means here, so that one is here, so maximum breakdown, maximum collector emitter breakdown voltage when base current is zero, and next what about VCBO 0 means the maximum collector base current base voltage breakdown when when emitter current is 0. Now here this is regarding output characteristics, and next here this is hard saturation. Next, safe operating area of power BJT. Safe operating, before going to explain the safe operating area, first I want to explain primary breakdown and secondary breakdown. Primary breakdown means here in the primary breakdown, because of avalanche breakdown of emitter, avalanche breakdown of collector base junction. So now here, because of that power is dissipated, so now power diode may damage. What about the secondary breakdown? Secondary breakdown means here power BJT is a negative temperature coefficient. Negative temperature coefficient. We know this IC equals to alpha into IE plus ICBO. This is the leakage current or reverse saturation current. So now this ICBO is double for every 10 degrees centigrade rise in temperature. So now here from this we can say that P equals to V into I. So power equals to V into I. So now here temperature rises means here ICBO increases. So temperature rises means IC increases. IC increases means ICBO increases and IC increases means power is increases. So power is increases means again temperature is increases. So now here again collector current is increasing. Now here current is increasing just because of negative temperature coefficient. So now here negative temperature coefficient and current is increasing over the same area in the power BJT. Current is increasing over the same area that results in hotspot, local hotspots will create. So hotspots. So because of this reason, so power the hotspots may cause for secondary breakdown. So huge amount of power is dissipated. So power BJT will break down. This is regarding secondary breakdown. So now here we know this P equals to VCE into IC. So maximum power equals to. So now here if you apply logarithm of P equals to this is log of VCE plus log of IC. So now this is in X plus Y format, means that is straight line. So this is power straight line. So now here, so this is maximum current limit A, B, C and D, and this is a maximum voltage and this is the maximum power or temperature, and next this is secondary breakdown. So this is in logarithmic table only. Log of C if you draw the graph between. So now this is safe operating area. So what do you mean by safe operating area means here? So now here the load line, these are the output characteristics. So now VCE and next this is IC. So this is load line. So now the operating point. So now the operating point means where the intersection of output characteristics and this load line is the operating point. And now here when transistor, the power BJT operates in safe mode, at all the all the operating points is known as a safe operating area. So now here this is maximum current, maximum power, secondary breakdown and maximum voltage. And next here, this is for continuous. So here this is for continuous and this is for pulsed. This is for pulsed derivative. And next here it operates in two modes. So forward bias safe operating area and reverse bias safe operating area. So this already we have seen, and in this here, so during turn off, So the transistor is subjected to high voltage and high current. So now when VBE is in reverse biased, so it is drawn between same IC and VBE. So the graph, this is for IB equals to 0. This is for IB is less than 0 means is -1. IB equals to -2 in negative. So now this is same for current and this is for voltage. Now the most important is switching characteristics of power diode. So power BJT we can use as a switch. We can turn on, turn off. So it is divided into turn on characteristics and turn off characteristics. So first we will see. So now here power BJT. So power BJT, first base is negative voltage, that is V2 minus V2 voltage we are applying to the base emitter, and during that case no current. So no current means VCE equals to VCC and IC equals to 0. IC equals to 0 and VB equals to same minus V2. VB equals to minus V2. So now here there is a leakage current. So because of the there is a leakage current. So now here we are giving. So this is because of there is no current. So here, so now I am giving a positive voltage V1, and next next here this is IB1, the IB1 current I am giving, V1 voltage is given, IB1 current, and next here when we give a positive voltage to the emitter base junction, immediately it will not turn on. So because of transistor junction capacitances. So now here, so when it will reaches to the 0.7 something, means to charge the junction emitter base junction capacitance, there may be some delay, some voltage VBES. So emitter base junction voltage, to charge the emitter base junction capacitance voltage to some voltage 0.7. So that to take that time, that is delay time, and during that time, so now this leakage current, initially it is 0, that leakage current to 0.1 percentage of ICS. So now if it is ICS current, so this leakage current is ICS current. So now this is VCC. So now VCE equals to VCC when there is no voltage, and now here this current, and this is 0.1, and next here from VCC to 0.9 VCC, and this is 0.1 ICS. So now this is delay time. Delay time means here, this is delay time. So this delay time means here, this I am writing here, from ICS, from leakage current to the initial value, to leakage or initial value to the 0.1 ICS, or VCC to 0.9 VCC. So here time taken to reach from leakage current to the 0.1 percentage of 0.1 means 10 percentage of ICS, or time taken to reach from collect VCC voltage to 90%, 0.9 VCC is known as a delay time, R. And next, rise time. Rise time means here, so from 0.1 to 0.9 ICS means 10 percentage to 90 percentage. Same way, completely opposite, from 0.9 to 0.1. So now rise time means here 0.1 to 0.9 ICS, and next 0.9 VCC to 0.1 IC. So when any switch is turned on, current is increasing and voltage is decreasing during turn on. Voltage is decreasing from VCC to 0.9, this is delay, and 0.9 to 0.1, this is delaying, and next here decreasing, and next from leakage current to the 0.1, 10% ICS increasing, and from ICS to and 0.9 ICS. So now current is increasing. Now turn on characteristics, turn on time means here TD plus TC. Turn on time means TD plus TC. Turn on time means TD plus TC. TD plus TC. So now here another thing, now here this is rise time. This duration is rise time. Next again this transistor turn on equals to TD plus TC. Again now here this is conducting period, conduction time, this is conduction time. Next now to turn off the base junction must be in reverse bias. So now for that case, so now here this V1 is again apply V2 and this current is minus VB2. So now immediately it will not turn off. So there may be a charge carriers in the junctions. So because of that immediately it will not turn off. So now because of that reason, so now that is storage time. So storage time means here, so this is not delay time, storage time. Storage time means here, in the storage time here from the ICS to 0.9 ICS means maximum this ICS to the 90% of ICS, and next here 0. VCC to VCS to 0.1 VCC is known as a storage time in this period. So the total excess amount of charge carriers will be removed. So now that is storage time. So now here rise time means 0.1 VCE, this is VCE, yes. So now VC 0.1 VCE yes to 0.1. Now here, so 0.12 and 0.9 VCC. So this is the fall time. So now here, so now 0.9 to 0.1 ICS. So now here we have two definitions. So storage time is defined as, so not delay time, one is fall time and this is the term of storage time. Storage time means here, so 0. ICS to 0.9 ICS, and next here 0 to VCC2, sorry, some saturation voltage VCES to VCES to and 0.1 VCC. So that current, the time required to reach between these two is known as a storage time. After that, so now here fall time means here, so here 0.9 ICS to 0.1 ICS. So time required to from this current 0.9 to ICS. Current will decreases in off time and voltage will increases. Same way 0.1 VS2 saturation voltage current, and next here 0.9 VCS. So now this time period is known as a fall time. So now TS plus TF, fall time plus storage time, is known as a turn off time. Though this turn off time is represented with Q, and TC means circuit turn off time. Circuit turn off time is always greater than this device turn off time TQ. So now this is regarding switching characteristics, and next here this is TF, and TS plus TF equals to turn off time, that is TQ. So now here coming to the advantages, it is a bipolar device. Already we discussed bipolar device means conduction takes place in this device because of electrons and holes. It has short turn on and turn off time. So means short turn on and turn off time means we can use it for high frequency applications up to 10 kilohertz, and delay time it can be available easily and less cost, and base drive has full control over the application of BJT. It does not require any commutation circuit. It is a fully controlled device, power diode. So any external commutation circuits, class A, class B, class D, so all these are not required. So now here in case of thyristor SCR, we need commutation circuit, but here it will not require. It has small turn on losses. And next, permitting size reduction of electromagnetic components, and after that it can provide current limit protection by base drive circuits. And next, what about the disadvantages? So drive circuit for BJT is complex, and storage charge in the base reduced switching frequencies, and it has negative temperature coefficient. So already we have seen in the, because of negative temperature coefficient, the ICBO reverse saturation current doubles for every 10 degrees rise in temperature. So because of that, collector current increases. Collector current increases means overall power increases. So now because of that, secondary breakdown will happen. So this creates the problems in paralleling of our BJTs, and next it suffers from secondary breakdown. Because of this negative temperature only it will happen secondary breakdown. Thermal run away is possible. And next here it requires continuous drive during on state. So it requires continuous drive means losses are more. And next, what about the applications? So it is used in the SMPS switch mode power supply, and power amplifiers we will use in the relays. In the drivers we will use the AC motor, speed controllers we will use AC to DC to AC, that means inverters, and DC to DC, that means choppers we will use. And that one last one is as series pass transistor in the regulated power supply we will use, and that last one is the audio amplifier in the steering system and power control. And next, power factor correction techniques we will use. I hope all these techniques are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.